All right. So you know about the lab. One thing I would highlight for ventilation stuff is if you do end up going into the field, we do have, or you just have a project where there's complaints about ventilation or fresh air. We've got a flow hood, and manometer. It's basically like a mini fan that you can hold up to the vents. CO2 monitors, particulate matter monitors, like the purple air ones, for wildfire smoke, and then ozone. And those are all free for you to check out, either for a project that you're doing with Cushing Terrell, or even just your house. I've used them all in my house. Yeah, no, it was really helpful for me using the flow hood, going around and like measuring the output of all my vents, and to see like I did not need twice as much air coming into my tiny half bath as I had into my living room. Like,
I had the same thing. I closed the vent. I was like, this is ridiculous.
Yeah. And then we've got little temperature loggers, so you can stick them into the different areas and see where they go.
Yeah.
Anyway, it's a free resource. We'd love people to use it, so feel free to check it out. And then we've got, this is December 11th.
My birthday.
Oh, that's nice. So you might not want to spend your lunch here, but if you do, or you need CEUs, there's free lunch, and it's an ASHRAE joint lecture with.
Yeah, I just got an email about that one.
Cool. I think it'll be really, really good. It's a good speaker. She's a distinguished lecturer for ASHRAE. And Cushing Terrell, they're really good at energy modeling. You guys were one of the leaders in it.
No, we're really good at that.
Yeah. I really admire the work that Tim Johnson does in there. Hey, welcome.
He does a good job. He's showing me some of the stuff.
And using energy modeling is one way to meet parts of this code, just like we talked about the envelope last time. So I think she'll be touching on that a little bit. And if you're interested in getting into energy modeling or part of that team, I'm pretty sure Tim will be there. I'm probably biased, but I found it just be very helpful to use energy modeling for a number of different reasons. And part of it is that it makes code compliance a lot simpler.
Yeah, that's good. I'm pretty sure we do everything for the most part with this, at least a small one.
Yeah.
I model every building, do ventilation pumps up there.
Okay. Oh, well, right. So you're checking the numbers and making sure everything.
Yeah, I actually build a model of the building and then have run. We're switching. We were using train trays, so it's just a 2D version.
Mm-hmm.
And we're switching over to a new product that we're testing it with not as good as train trays. So we're not sure if we want to do it.
Is that Cove or?
No, we're shoot, which one was it? Cap. 6.2.
Okay. Yeah.
Yeah. So we're finding some bugs in it.
Okay. So for today, I'll be going over basically this 2018 IECC. Looking ahead to future codes, at least the 2021 doesn't change a whole lot from this. So even though I'm trying to make this Idaho specific, and you might be doing projects around the country with different energy codes, if you're using the 2021 IECC, in terms of ventilation, it's pretty much identical to this one. I'll type out economizers, DCVs, ERVs, and then parking ventilation too. What's interesting is IECC, it's very closely tied with ASHRAE, which develops the 90.1 set of energy codes. And ASHRAE is often advocating for increased outdoor air, like proper ventilation, from a health standpoint. But from an energy standpoint, like the more air you bring into the building, the more energy it takes to heat up or cool it down. So there's that tension. And so from the energy code, it's not about necessarily pulling back on the fresh air. It's more having the ability to pull back on the fresh air. A lot of it is about controls. And I used to give the presentations with the slideshow that showed what happened cognitively with high CO2 levels, that, you know, our bodies start to get a little more lethargic. It's harder to concentrate on tasks and things like that. But as I was prepping for this over the last couple of weeks, there's been some pushback on that original study that came out. And so there's really kind of mixed conclusions on how much we are affected by CO2 levels. Part of that study came out of like doing natural experiments with masks. Like people were getting super high concentrations of CO2 when wearing masks, and yet their job performance didn't change a whole lot. There is still some physiological things that happen. I mean, if we get super high doses of CO2, it bypasses what's the hippocampus, basically our fear center, and it makes us super terrified that we're not getting enough oxygen. Even if you have enough oxygen, if you have a super high dose of CO2, your brain's going to think that actually I need to start gasping for air and yawning and things like that. The book by James Nestor called Breath is really fascinating if you kind of look at that. But in terms of buildings, we're generally not dosed with 10,000 parts per million of CO2 in our faces. It's more about, you know, how do we keep enough fresh air in the space? Whether going above 1,000 parts per million, which is kind of the ASHRAE standard, really starts to impact performance or not is up for debate. I personally would love just more fresh air and flushed buildings, using dedicated outdoor air systems. But one way we can talk about that is to look at removing the CO2 rather than just ramping up huge amounts of outdoor air. So kind of targeting some of the contaminants. So the ventilation that is required, the minimum you need to bring in, it's in the, if you look in 2018, it just jumps you over to the mechanical code, the IMC. And the International Mechanical Code also references the ASHRAE standard 62.1. You can, I would stick with the International Mechanical Code. The ASHRAE code does update every so often, but the IMC does a pretty good job of just condensing everything into one table. In ASHRAE, it's kind of separated between ventilate or exhaust zones and supply zones. And here in one table, you get everything at once. And the three main things that you need are, you know, the people flow rate. You need to know what the occupancy is going to be in that room. The area, which you then also add in that extra ventilation just for the amount of area, and then whether that space needs exhaust or not. Certain occupancy areas do need exhaust, like art classrooms, for example, whereas regular classrooms don't, but because there's fumes there, or if it's you know, bathrooms and things like that, then those have certain exhaust requirements. So if the goal is to, you know, have good clean air and also save energy, like how do we target some of the pollutants so we don't have giant vents or open windows to the outside when it's 0 degrees out? So there's a number of suggestions. You won't find it strictly in the code language, but if you look at the code commentaries, they have a few design techniques to help minimize the amount of ventilation. And I'm calling this the skunk problem. Like, what do you do if there is a skunk in your building? Maybe that's a trash bin, maybe it's, you know, bathrooms, anything that you don't really want to be smelling, right? What can you do to get those odors out, or get those chemicals out without just blasting it with tons of air? One is just target the source. So identify and remove the skunk. But if that's not an option, if you are just going to have that storage room, which might be an evidence locker, in a sheriff's office that has some contraband in it that's very, very smelly, which we've encountered multiple times, and that smell gets spread everywhere through the office, is instead to contain that. Have localized exhaust for that area, fence in the skunk. The other is to have an alert when the skunk is in the building. So, that's carbon dioxide, carbon monoxide, or particulate matter, or even just the number of occupants within the space. If you have demand control, then you can scale your ventilation more appropriately. The next is to, bring in something that smells nicer and dilute that skunk smell. They call it transfer air. So if you've got a large space next to a smaller smelly space, then try to, force the air the proper direction into the smaller space to dilute it. And then the last one is to just be very effective at the airflow in terms of removing that skunk smell. So in this room, we've got actually a really good ventilation system in terms of removing odors and germs and anything else airborne, because we've got underfloor air distribution. So we've got supply. It is noisy because of the pressure in this building and that it's really hot back here. So it's a little bit oversized. So I have to speak over the hiss of the things, but it means that you're getting lots of fresh air. And so this is clean supply air coming up. And if I sneeze or something, then it's going to go straight into that ceiling register and out the building rather than getting spread straight to you guys, which is probably not what you want. So systems that work well, would be underfloor air distribution systems, or displacement ventilation is another one. And particularly dedicated outdoor air systems where you've got clear pathways from supply to exhaust without just mixing everything up together. Right. So that's some minimal ventilation techniques, targeting, containing, alarming, or diluting the skunk, and then having a good exit strategy for that air. The other requirement that we have from code for ventilation is economizers. And economizers, if you're using the performance, the energy modeling method, then this is not necessarily mandatory, which is nice. The code is really pushing towards that total building performance method. And if your energy model shows that you're saving 15% of the energy costs within the space, then you're good. You get away with a lot of different changes to the envelope, and you don't have to worry about economizers, which there is kind of a long logic tree behind economizers that we'll go into, so you can just kind of remove that headache. And economizers can also be really expensive. So it might be worth it to the client to invest time and resources in an energy model rather than an economizer, as long as it results in utility savings. So when do you need them? You don't need them if your capacity is less than 1.7 billion BTU per hour. Or if it's just a part-time operating system, or if it's a supermarket with open refrigeration, or where there's a heat recovery system that's installed. So this is kind of where to start with these systems. Is just check the box. If you meet any of these criteria, then you don't have to worry about economizers. You can move on with the rest of your design. Now, it still might be worth it in terms of energy savings, but the way the code is developed, Pacific Northwest National Lab does a lot of energy modeling. And when they make a code recommendation, they're trying to do it on an economic basis to make sure that there is payback. They're not just doing something expensive that, yes, it saves energy, but it's never going to pay itself back. And economizers, because they're expensive, because the controls are expensive, they do have pretty limited requirements for them because it might not make sense economically. So if you are in one of these situations, if it's a pretty small system, or there's a lot of humidity within the space, which would be, you know, your Whole Foods right across the street, or where you've already got a heat recovery system in there. The economizer is not going to provide enough bang for your buck, essentially. So you don't necessarily have to use it. There's also exceptions for areas with process loads that have certain humidification requirements, which would be like storing produce or things like that, where you need to keep the dew point above a certain temperature. But why do we use them? They're really good for Idaho's climate. So it's a way of just opening up and allowing outdoor air to do free cooling for you, rather than taking, you know, the exhaust air that's coming out of the building. That's, you know, during the summertime, say, that's maybe 75 degrees, but outside in the mornings, it might be 50 degrees. So instead of trying to cool that 75-degree indoor air down, just exhaust all of that and just bring in all this fresh, cooler air, so you minimize your chiller requirements. So it's ideal when you have cool, dry air during the day between 8 a.m. and 4 p.m. When it's between 55 to 70 degrees Fahrenheit out there. And that happens in Idaho's climate quite a bit. We're climate zone 5B and 6B, which means we're cool and dry. So when you're designing buildings in Idaho, we've got more economizer requirements than we do, say, in like Florida or somewhere else. It's just too humid and too warm. One project that our lab did, this was a number of years ago, was we built an energy model as a digital twin of a Moscow campus building. It was a classroom, pretty large building that shall remain nameless for reasons you'll understand shortly. But we realized that they never had their economizer going. They had one installed, the controls were there, but it was completely locked out. It would never actually bring in that cool morning air. And the facility managers were kind enough to give us direct access. And so we started messing with it, and we were looking at it on a morning like today, and it was like, hey, this building is, I guess it was a summer day. It was supposed to be in cooling mode, and we should be bringing in some outdoor air because our sensor was saying it's like 60 degrees outside. And instead we're just, you know, trying to cool down the 70-degree indoor air and recycling. We should just bring in some more fresh air and cool it down. And as soon as we did, we saw all the thermostats in the building like pop up to like 80 degrees and things like that. People were probably miserable. So very quickly, like within 5 minutes, we're like, nope, not going to do that. Turn it off. And the reason was, then we looked at Moscow weather, so we were down here, and it was actually like really hot outside. But the sensor made it look like it was cold because the sensor had been installed close to the rose bushes and the sprinklers were hitting it every morning. And so it was like cooling it down, making it think that it was like 20 degrees colder outside than it was. So they moved that sensor, that's all that it took, and then reactivated the economizer. But we found that by doing that, they would save about 50,000 kilowatt hours a year, which is about $4,000 in energy costs. And, you know, $4,000 isn't huge, but you think of the number of different buildings, commercial buildings in Idaho. And if none of them had economizers, that adds up to a whole lot of money pretty quickly. You have 100 buildings like that, that's $400,000, right? And so that's why we have these requirements in the energy code. So this was kind of a cool example to see, oh, actually there's a reason to have these functioning in Idaho. So what do you need for your economizer? Essentially, you need to open up your damper so it can provide 100% outdoor air. This isn't like the total capacity of your supply system. It just means however much outdoor air you might have. Typically, it's dialed down to maybe 30%, and it's mixing with the return. It needs to have the ability to open up to that full 100%. And for the controls, the damper needs to be managed. It's not just controlled by the mixed air temperature. It should be linked with the cooling system, because the idea is that you turn your cooling system off, so you're not needing it as much when you're bringing in this cooler outdoor air. But once it gets warm, there should be a high limit shutoff, right? That's what we were doing accidentally when we were messing with the building in Moscow. Like we were actually bringing in like 90-degree air and roasting everyone because it was interlocked with the cooling control, so it wasn't cooling that air down, right? So there should be a high limit shutoff, assuming that your sensor's not getting sprayed with irrigation water. So once it starts getting warm, then you start dialing the amount of fresh air back to its normal minimum. Because it's an energy saving measure, right? Because we're recycling a lot of our heat, and if the exhaust air from our building is 73 degrees and outdoors it's 80 degrees, then it doesn't make sense for us to hammer our chiller and bring in all 80-degree air. Let's mix a little bit of it. Unless, of course, you're using a dedicated outdoor air system, in which case you're always bringing in just 100% fresh air all the time. And those are the systems that I really love. It also needs to not overpressurize the building. So there needs to be an exception, basically a relief outlet, so that the fan doesn't send all that air through the building. Otherwise, like your elevator doors stop closing and other doors start closing. So making sure that you don't overpressurize the building when the economizer is active, just a little relief valve is required in there. And then making sure that your dampers don't leak as much. There is a separate requirement later on in the code for dampers and where they need to be. So the leakage rate is not greater than 4 CFM per square foot of that damper area. The idea being that, we have this damper and it's going to open all the way when it's ideal for us. But during super, warm summer days, we don't want this like 90-degree air just leaking into the rest of the system and overcooling the space. You could have even tighter dampers though, like passive house requirements has dampers specified at just 1 CFM per square foot. So, but this is like the bare legal minimum that you do need on your dampers. So that's economizers. In terms of demand control ventilation, this is mandatory even if you do use the performance method. So the performance doing an energy model doesn't get you completely free of the rest of the energy code. There are certain requirements that are still mandatory, and this is one of them. So this is just managing the ventilation so that we're not bringing in tons of cold or hot air when there's nobody in the building to breathe it or notice it. But it's only if your space is greater than 500 square feet for that zone, and if you have more than 25 occupants per 1,000 square feet. So if you've got a huge warehouse and there's not many occupants, you don't have to worry about it. Or if it's just one small zone that's less than 500 square feet, then you don't have to worry about demand control. But you do have to, if that's not the case, you've got a larger space and it's got a lot of occupants, a classroom, for example. You are going to have to put it wherever there's an economizer, there's automatic outdoor dampers, or the outdoor air that you're bringing into the space is 3,000 CFM or greater. So that's kind of the part of the logic tree. It's also not required for if you've got energy recovery present, which I'll go into next. If you've got multi-zone systems without direct digital controls, a centralized control system, then you don't need to have demand control ventilation. Or if your outdoor air is, that should be less than 1,200 CFM. Or if your supply air minus your makeup air is also less than 1,200 CFM. Or if it's just process loads rather than like occupant loads for ventilation. So, and I'll talk about this at the end too, but there's so many, I'm trying to simplify like when these things are applicable and when they're not, because sitting down and reading the tables is pretty mind numbing. to be honest. So I just encourage you to, like, when you've got a new building, when you've got a design, just have those criteria in front of you. Know your occupants for your zones, know your spaces and their sizes. And then from that, calculate your minimum outdoor air CFM so that you can do a quick check. If it's an Excel table, you can filter for, okay, well, if it's less than 1200 CFM, great. Then I'm not going to have to worry about demand control ventilation in that zone or something like that. Or ERVs or an economizer in these certain settings. So yeah, just have that either on a separate screen or print it out in front of you on your desk when you're going through it. And it'll help make going through the code book slightly less onerous, hopefully, and a little quicker to get through to the actual fun part of design. So for energy recovery ventilation, this is interesting because on the residential side, there's not a requirement in Idaho right now, but if we switch to the 2021 or the 2024 code, it's going to start to be required, which would mean we put HRVs into homes, which I think would be great, but it might also be expensive. So probably be some pushback on that. But it's an incredible technology in terms of energy savings. It's a way of recycling the heat from the building without necessarily mixing air streams. You've got your exhaust running out and your supply coming in, and they're going right next to each other, next to some good heat transfer coils. And so you get to just exchange heat without exchanging contaminants. There's different levels of effectiveness. Like if you just have two pipes next to each other, obviously you're not going to exchange a whole lot of heat rather than a whole bunch of tiny fins and tubes and well-designed systems or an enthalpy wheel. So there is a minimum effectiveness for heat exchangers. They have to be at least 50% effective on a total heat transfer basis, which means both air temperature and the latent energy that's available in the humidity. But you don't need them for kitchen exhaust or labs where you might have some corrosive particles or grease that would clog up the heat exchange coils. It does need an economizer bypass. And if you're operating less than basically 24/7 in climate zone 5B, which is most of Idaho, there is no requirement for ERVs. So you get away with that, which can save some money. If you're in climate zone 6B, which would be like your Salmon, Idaho, or Pocatello, or Idaho Falls, as we're starting to get closer to Montana, then there is a requirement if it's greater than 1500 CFM. So there's 8,760 hours in the year. So if you've got any building that has, you know, some holiday breaks and times when it can be shut down and things like that, then you can get away without necessarily having ERVs. But if it is required to operate basically 24/7, all the year round, the requirements get way more strict. And it depends on the percentage that you're bringing in from the outside. There's, if you're bringing in 80% or more outdoor air, which would be like a dedicated outdoor air system, which would use with heat pumps or a VRF or you know, even a radiant system. At that point, for 5B, you definitely do need an energy recovery ventilation system. But if you're bringing in just a little bit, say 10% to 20% of outdoor air, and you're recycling the rest, that would be a, you know, your variable air volume system, your typical rooftop system. Then you don't need it unless you have more than 2,500 CFM. And it's once again far stricter in climate zone 6B. The reason it's strict is because it's darn cold up in Salmon during the winter time. And it's a great way of capturing heat when it's 0 degrees outside and you're exhausting 70-degree indoor air heat. With 50% effectiveness, you're getting like a huge boost in terms of energy by recovering some of that heat. So that's why they have a stricter requirement there for energy recovery ventilation systems. Then we've got enclosed parking garages. And the parking garage ventilation, once again, it refers to the International Mechanical Code for when it's required. IMC requires a minimum ventilation rate of 0.7 CFM per foot squared. So to kind of doing some quick math, I should have put it directly on the slide. If you have a garage with 22,500 CFM and it's meeting that IMC, it's basically a garage that's if the garage is less than 30,000 square feet, then you don't need this. You don't need these controls, I should say. The ventilation is still required by the mechanical code, but you don't have to have these interlocking controls. And there's another exception. If your ventilation to horsepower ratio for your exhaust fans is greater than 1125 CFM per horsepower. What these require you to do is to not choke on car exhaust fumes, but to just have the fans shut off when they're not needed. So they've got some controls in there that's sensing probably carbon monoxide as exhaust. Or if they operate intermittently for less than 20% of occupied time, when you know that there's going to be cars in the building. One important thing on these controls is that they fail to on, so that if for some reason the sensor's failing to send signals, then the fans just are going to operate 24/7 to just for safety reasons to exhaust anything out. We have these controls in the basement in our parking garage down below. So if the fans randomly turn on and the damper's open and you hear this huge whoosh, which terrifies me in the middle of the night sometimes when I'm walking home. It's because they're on a timer that operates every so often, or one of the carbon monoxide sensors. So those controls are required according to the energy code. Otherwise, the mechanical code says the mechanical code is concerned with just having those fans in there. It doesn't care like when you shut them off, and from an energy standpoint, it matters a lot. There's also regulations in the efficiency code on the ventilation air that you're bringing into the building. If it's a summer day, you've got fountains going on at the Grove, and your building is in cooling mode, then the outdoor air should not be heated above 60 degrees Fahrenheit. So this doesn't apply if it's like a semi-heated space, like a garage or an equipment bay that only has heating. This applies to buildings that have both heating and cooling, and the majority of the building is in cooling mode. Now, how do you know that the majority of the building is in cooling mode? Either you've got an energy management system that will calculate like the number of zones that are in cooling versus heating, and it will trigger this this control, or you can just have it based on the outdoor air temperature, and that's going to trigger not overheating your outdoor air that's coming into the building. You generally do want to have the outdoor heated for ventilation, at least to a certain extent, especially in a dedicated outdoor air system, because people don't love the feeling of a 40-degree draft on their neck of, when they're sitting at their desk, when you're supplying that. So if you have your heating and cooling separate from your ventilation air, that's why they try to maintain closer to like a 60-degree temperature. But if your building's in cooling mode, then we don't need to basically preheat our air only to cool it down later. That's what they're trying to prevent. They're trying to prevent your building from doing double the work during the summertime, which might happen if you're trying to drop some humidity out of the air. Other controls that you might encounter in Boise, large hotels. So this is residential or R1 occupancy with 50 or more guest rooms. This requires unoccupied guest rooms, the ventilation, the fresh air to shut off after 30 minutes when people leave. And it can have a 1 hour purge cycle of fresh air, maybe after cleaning or something like that, before people arrive. It doesn't say exactly what kind of controls are required in order to do this, like how you're measuring this. This could be an occupancy sensor within the room that's detecting motion, or your key card systems. Hotels in Europe, you kind of have to put your key into the slot once you go into the room so that it shows that the room is being occupied, and then you have to take it out when you leave. Or even if your hotel has software showing which rooms are booked and when, all of that can work. You just have to argue to the code official, here's your design intent. We're going to manage it X way, but it has to be managed some way to provide some shut off so that we're not bringing in tons of outdoor air to rooms that are just vacant over a long time. But that 1 hour purge per day should also count for the hotel staff doing cleaning and making sure that we get the chemicals out as well. All right, so takeaways for today. Once again, have the information in front of you when you're going through some of these logic trees. Start with what you know, the zone sizes, the ventilation loads, and then minimize ventilation by targeting pollutants. Are you gonna target, fence, alarm, or move the skunk to another room, or just have better airflow around it? So you're not bringing in more air than you need. Economizers are great in our climate as long as there's good controls. You kind of have to follow the logic trees for demand control ventilation and energy recovery ventilation. And then consider performance modeling. See if you can get more savings, save on capital costs. And one other plug for using energy models is that if you have a model for your building, there's a lot of software that will have a code compliant button or measure within it. I know OpenStudio does. And it will follow these logic trees for you. So you can say, okay, here's my geometry, here's my space type use, generate for me my code compliant building, basically your worst building that you can legally build. And it will populate when it has economizers in there, when it's got heat exchangers, the different types of controls. So you can actually see if you missed something along the way. And you might do something different in terms of the performance modeling to try to get that 15% savings. But that baseline model can be super helpful to just make sure that you didn't miss something that the code might come back on and mention to you. So just another reason to consider using energy models is just a double check to make sure that you didn't miss, say, ERVs in a particular climate or something. Anyway, that's what I've got for you guys today. If you have questions or have a project that comes up and you're stumped on what this language means or whether there's one requirement conflicting with another or something like that, please feel free to email me and I'll do my best to investigate it, or have a grad student get to work on it too, so they can get to know the code. That's kind of our model here at IDL, is to try to give students real world problems that you might not necessarily have time for, but they can do the investigative work for you. Any questions that you guys have? Cool. Well, thanks for showing up. Appreciate it.